So we have two strings, the source and the target. And we have some transition metrics like original and what's the name? Original and changed. And the cost associated with the change. So, for example, original B and change to C, and the cost, for example, of 2. These are separate pairs or triples. So C, D, like 5, and so on. EH is 10. And they can also be quite repetitive and overwrite itself, so like this. So we have to be careful. Now we ask to find the minimum cost to change source to the target, if it is possible. The length of the source and target is 10 to the power of 5, and the length of these transitions is 1000. So the algorithm is first we want to find how can we do this transition. For if the char is equal, we can skip it, so no cost. But if it's not, we have to find the optimal way to transform one letter to the other. And if we're lucky, we would have this transformed directly, like this one. B to C is 2. But if we're not lucky, there are jumps we have to make. For example, D and G, like this. From imagine we have D to E, and then from E to G. These two transitions we can make to finally jump to this one. So the problem can be transformed to the sub-problem of how can we calculate the optimal transition from one letter to another for all the possible letters. So this cost from the same letters as 0, and there are some transitions that are possible and some that are not possible. So from C to B, for example, the cost would be 1, and there are some not possible costs. We can mark them as infinite. So this is a transition matrix, and we want to find it given this 3 arrays: original, changed, and cost. We want to find this optimal transition matrix. It should contain the final cost of optimal transition from one letter to another. The go-to algorithm is Floyd-Warshall, and this algorithm is about DP, dynamic programming. So imagine we have transitions like from A to B, like this. we're given this transition, and there are possible some it is possible that there is exists some intermediate value like k, or I will call it c, that this transition would be more optimal. And the Floyd-Warshall allows us to actually do this kind of improvement. So we iterating. We must be careful to iterate with correct order. Values a, then values b, like 4, 4, and then some intermediate values. So the matrix transition of from A to B is the minimum MA to B, or some intermediate value, like for example C, M from A to C. I would mark it this orange, M A to C, plus M from C to B. So this kind of update we make. Now the tricky part of this algorithm is this is not actually a relaxation. It is not the relaxation. If we want to do the relaxation, we should to consider for A, for B, for C intermediate value, and relaxation for relaxation. And this relaxation should be made of path lengths. So in any path we make at least one relaxation. So this would be algorithm without any idea behind, just to relax a single jump, and we should make at most the length of the path this kind of relaxation. However, the Floyd-Warshall algorithm, it's kind of DP algorithm, so the trick is that we put the intermediate here before any other relaxations. So that means that if we this C value is how many other intermediate values you have considered. For example, if it's from A to Z, and if the letter A was already in the middle, we wouldn't check it anymore. So only once it can be the middle. So my accepted solution was a relaxation algorithm. It was accepted, and this C intermediate value I use it many times. So as you can see, it's in the inner loop. So you have to try every time, for every edge, try another time, and you have to do this kind of R, or relaxations. R stands for the relaxations. So it's kind of a little bit slower, but is accepted because the length is small. However, the optimal would be, of course, this one, and its original Floyd-Warshall. And to remember the idea behind Floyd-Warshall is that the middle only once. And if you have this idea in your head, you would know that you have to put the middle here in the outer loop. This is the only way you can make sure that it is used only once. Now, this problem has solutions with Dijkstra, but the algorithm is kind of extra long, and I don't like this. This priority queue is overhead for this kind of problem. Now let's look at my little bit optimized solution. However, it is almost as compressed as it can be. There are solution. I tried to fit the entire code with lengths of the method length. So in Rust you can have arrays instead of vectors, and this is 97 trick to instead of character A you use 97, and also trick with zip to avoid as bytes casting, and trifold to return early if you had the unvisited edge. Now the Kotlin version, it is this one. It is the same, but only four lines of code compared to the first iteration. So this is the three loops, and it is optimal. It is the middle in the outer loop, as you can see, and take if to return early. The Kotlin allows you to return from the sumOf. However, the Rust is forbidden to do this in Rust. So that's it for today.